Welcome everyone. In this video lecture, we will solve a problem which is basically MOSFET circuits at DC. So it is the problem. It is from the Microelectronics circuits book. So the question is design the circuit for the below figure. So this one is the figure given and this one is a NMOS to establish a drain voltage of 0.1 volt. So this VD is given 0.1 volt. RD value is unknown. So what is the effective resistance between drain and source at the at this operating point, and given thing is Vt 1 volt and Kn dash W by L 1 milliampere per volt square. So first of all, in this question we have to write the given thing. So the given thing is the VDD value is 5 volt, VD value is 0.1 volt, okay, VT value is 1 volt, and K and dash W by L is 1 milliampere per volt square. Milli, this one is milli 10 to the minus 3. So these are the things given. So the we have to find first the value of id for the operating point region. Id is unknown, so we have to find the value of id. Also we have to find the value of rd for this design of the circuit. Id value, and a small rds, the resistance between the drain to source in. So these are the key things that we have to find. So first of all, in such type of problem we have to identify in which region the circuit is operating. So in which region, it may be either linear or saturation, okay, it may be cut off. So we have to identify. So for that thing we have to know the basic concept that if the VDS is greater than equals to VGS minus VT, this was is in the saturation region, okay, saturation region. And if the VDS value is less than VGS minus VT, it is in the linear region, okay. I have already mentioned the curve for this one in the my last video. Means if we plot id versus VDS curve, it looks like this, a high pass filter type response, and this should be will be the saturation. So here this should be VGS minus VT. If VDS is greater than VGS minus VT, then it is in the saturation, and in that side it is in the linear region, okay. I have already discussed this thing. So these two are very important thing. So first we have to identify in which region it is working, okay. So what I am doing, simply we can write here VDS, and here I am writing VGS minus VT, okay. The source in the VS is grounded, so no need to worry. So or one can write like this, VG minus VS minus VT, okay. I'm not mentioning the sign here. At the end we will, so this one will be 0, this one will be 0. So and VD is already given, or one more line we can write VD VG minus VT. So this VD is given 0.1, and this VG is directly connected to 5 volt. This is somehow this kind of a structure, 5 volt, okay. So this one is 5 minus threshold voltage 1, okay. So one can write this one is 0.1 and 4. So this one is less, okay. This VDS will be less, so this one is less, okay. So we can say now this one is in the linear region, okay. So first thing in any question we have to identify in which region this one is. So this one is in the circuit is in the linear region. So now if we know the circuit is operating in the linear region, so what we have to do now, we have to write the drain current equation in the linear region expression, okay. So now I am here writing id in linear, okay, can be written as k n dash w by l we have to know the formula VGS minus VT into VDS minus VDS square by 2. Okay, VDS whole square by 2, or we can write like that. So now we have to find the value of ID, the drain current, the current flowing through the RD resistor. So K and S W by L is already given, so 1 milli. So I am writing this one, K and S W by L. Okay, VGS, so gate voltage is 5, so 5 minus 0, so 5 minus 1 we can write, because VGS is simply our VG minus VS. VG is 5 volt, directly connected to supply, and S is 0, so 5. Okay, so 5 minus 1 I am directly like VDS is simply our right writing VDS. VD minus S, VD is 0.1 minus 0, so it's simply 0.1, because source is this, it is source 1, gate and drain. Arrow is in always the source terminal. So 5 minus 1 into 0.1. Okay, make it minus 0.1 whole square by 2. Now we have to solve this one. Okay, so what we will do, this one 5 minus 1 into 0.1, so we can simply write 0.4, 0.1 whole square, so we can write 0.01. Okay, 0.01 divided by 2. Okay, so make it 2. Then if we solve this one, it will come 10 to the power minus 3, 0.4 minus 0.01 divided by 2. So if we calculate, simply it will come like 0.0005. Okay, you can calculate this one through a calculator. So this one 0.4 minus this should be 0.395. Okay, so one can write this as a 0.395 milliampere. Instead of this device, one can write this as a milliampere. So this one is the drain current equation in the saturation region is 0.395 milliampere. So I am writing once again. So the ID value is now known to us, 0.395 milliampere. Okay. So now next, now we have to find the RD value. Okay. Now this current is our known to us, means this current is our 0.395 milliampere in this one. Okay. Some current is flowing through the RD resistance. So now what we are doing, we have to find the RD. So what we are doing, this one is RD, we have to find. This value is given VDD, that is our 5 volt, and this VD is already known to us, that is our 0.1 volt, and this current ID is now known to us, 0.395 milliampere. So using simple KVL concept or KCL concept, Kirchhoff's concept, or simple network concept, we can write this RD value will be current VDD minus VD by RD, oh sorry, ID, right, ID. So this should be our 5 minus 0.1. Okay, 5 minus 0 higher potential minus lower potential by this current will give the resistance value. So it should be 395 milli. Okay, so it should be 4.9 by 0.395 into 10 to the power 3. So it is in the kilo ohm range. So if we solve 4.9 divided by 0.395, it will nearly come around 12.40 kilo ohm. So the RD value will be our 12.40 kilo ohm. So this RD value is 12.4 kilo ohm also we can write. Okay, so this one is simple concept, higher potential minus lower potential by, means once again I am just, this is V1, this one is V2, and some current is flowing I. So this I current will be V1 minus V2 by R. Okay, or R equals to, if I is known, then we can write V1 minus V2 by I. Okay, so now we have already find the value of this ID and RD. Okay, so this one is ID and RD. Okay, now next we one more thing in the question that is asking, that is about the value of RDS, this drain to source resistance, drain to source resistance. Okay, so for this thing, that is our RDS value, what we will do, RDS. Okay, I have to select pencil. This RDS value, or we can write, yeah, better to write effective drain to source resistance, that is our RDS. Okay, this one for a small VDS, for a small VDS, that is our, simply VDS is our 0.1 volt. So this RDS value will be simply drain to source voltage by the drain current in the linear region. So VDS is known to us 0.1 volt, and ID is now known to us 0.395 milli. Okay, so better to solve this one. We can write it 10 to the power 3. This 10 to the power minus 3, if we put it in the numerator, 10 to the power 3 by 0.395. So if you solve this one, the total entire thing, it is nearly come 253.16, or better to write 253 ohm. So the RDS value will be 253 ohm. So this is all about this effective drain to source resistance, for the small VDS. Like that, we can find the value, effective drain to source resistance, RD value. Very simply, we can find the RD value, VDD minus VD by ID. So, and this one is the concept, means how to deal with it. So the drain current is now known to us. Everything we have the value. So now I am just writing the value, that what we observed here. The value of ID is around 0.395 milliampere. We can also write in micro also. So RD value is around, after solving, RD value is around 12.40 kilo ohm. Okay, and RDS value will be nearly 253 ohm. So this is all about this question, and this one is the question of a problem from a microelectronics circuit book. So this is all about the question of a simple analysis through which we can find the drain current is in, the circuit is in the linear or saturation region. Like that, we have to identify by using simple basic concept. So thank you for watching this video.